Okay, guys, any questions and any homeworks? I just glanced over a couple of homeworks here, and it seems that the one that I look at in the top, you are not doing a good job. So make sure that you know where we are coming from, and make sure you do the homework. And if you don't do a nice and clean job homework, then you cannot do the good job in the exam. So I'm not going to emphasize how important it is that you do. Some of them you do you left the cross product for me to see what that cross product here is, and you didn't finish it completely. So these are not acceptable. So the TA is going to make a notice on that one, and he writes it down that for a graduate course this is not acceptable performance. So I have a very high standard for myself, and I would like to have a high standard for my students, and make sure that you do a good job. So, and if you don't do a good job, then you will be in trouble. You will be in trouble. So make sure your homework is completely finished. Don't leave the cross product for me to finish it for you. All right? So then that's not good. Anybody homeworks? So any question from TA? So your homework is also graded, and Surush is going to take off. And thank you, Surush. And we'll see you next week.
They are graded homework.
All right. Graded homework is here. At the end of the class, please make sure you pick it up. We have around 60 students. How many students? 58?
Around 60.
Around 60 students in the class, and we have around 10 online probably. So the TA for online will take care of it and send it to online student. All right. We have quite a bit number of students here. Make sure you do a good job. All right. Any question from Surush? All right, if you have any question that you thought that the homework was not graded properly, talk to Surush, he will take care of you. All right, so let's keep on going. Any questions? All right, so last time we discussed about the, again, particle. Every rigid body is also particle. And we went ahead and we discussed about the concept of impulse and momentum. And what you had, we said that F is equal to d over dt of mv. Again, everything is a vector. Everything is vector. Now, if you multiply both sides of this equation by delta t, F dt is equal to dmv. Or if you go ahead and integrate this one from a stage 1 to a stage 2, from a stage 1 to a stage 2, and that is becomes mv2 number 2 minus mv1 number 1. And if your duration of impact is small, then you can say my force is not changing, and you can say F delta t is equal to mv2 minus mv1. So that's basically. And you can make a picture out of this one. You can say I have a particle, and you can say F delta t. Again, is a vector. Everything is a vector. Nothing is a scalar. F delta t plus mv is equal to mv2 number 2. And you can make a picture, and you can say this is by momentum. Then I have some impulse to here, F delta t, and as a result, it obtains new momentum mv2. So you make this kind of picture, and then hopefully, and once you make a picture, if you do have several impacts, then you can do for everything like this, and then you add them up. You add them up the right-hand side and left-hand side, and you have to do something. So last time we discussed about the case of the two balls that are coming at an angle, and that should be, we completely finished that problem. And we said the ball number 1 is coming with in this direction maybe, and ball number 2 is coming in this direction, and at some point they collide. When they collide, you have to attach the center line together, and suppose this is coming in this direction along the center line, And when it comes along that center line, it could be at another location, so it may be going this way. But you will still connect the center to center, and that's a point of impact. That's a point of impact that you have. So you can say that this is basically my object, and you can use this one as x, and you can use this one as a y. So it doesn't make any matter. If this ball is going this way, VB, and this ball is going this way, VA, and this is a mass MA, MB, and this is mass MA, no problem. You connect the center to center, center to center, and you try to put that problem. So you can say that if you connect the center to center, then it has a component in this direction, VAX. It has a component in this direction, VAY. This has component VBX and VBY. So, and if you look at the impact, then you say what happens to the particle A? The particle A is going in this direction, and you do have F delta T here, and nothing in this direction. Nothing in this direction, so that is basically impact. And the velocity is, for A, let's put the impulse first. So I like impulse first. So that's my particle is going MA VAX, MA VAY, and then there is impulses happening. That is the impulse F delta T in the x direction, and nothing in the y direction as long as the collision is a frictionless. So that's a y direction, x and y. And as a result of that one, the particle obtain new velocity again, MA V prime AX, MA V prime AY. So this picture plus this picture is equal to this picture. So you can see in the y direction, the only vector that you have is this one, nothing in this direction. So that means MAY must be equal to V prime AY must be equal to the MAY. So this vector, there is no vector in this direction, therefore that must be equal to this vector. So in the y direction is preserved. In the x direction, on the other hand, is not preserved, because you have this vector, you have this vector, and you have this vector. So now you can say that in the x direction, if I apply that figure, so I have MA VAX plus F delta T is equal to MA V prime A in the x direction. So that gives you one equation, and unfortunately you do not know this F delta T, and no problem. Yes? There is nothing in the dumb question in my class. Yes?
Is there, the impulse is coming from the mass B, right? The second ball?
Both balls collide together, they have action and reaction.
So if the component of if the ball B is moving in x and y, how come the impulse is only in the x direction and there's no y component?
Force is normal to the surface. So when you do have two balls like this, the direction of the force is here, that in this direction, normal to the surface. So the two balls come here, and that's what it comes. There is nothing in that direction. It is a frictionless. So when you have two surfaces come together, the surfaces that are contacting is in the direction of the connecting this center to connecting to this center. There is nothing in the y direction. The force has to be normal to the surface, and normal to the surface is here, that you have to connect to these two things together. Okay? There is no force in the y direction. It has a velocity in that direction, but it doesn't have any force in that direction. So that's the reason velocity is preserved. Are you with me? So there's a simple geometry. So when the two balls coming in some angle, in order to say where is a point of contact, the point of contact is this center to this center. You have to attach them together. And that is a line of action. Line of action. And that is the one that it collides this point, it collides to this point. And that's normal to the surface. So for particle B, if you do that, for particle B, it has a velocity in this direction, it has velocity in this direction. So you can say that for particle B, again, you make a picture, and you can say this is my particle B, and it's going in this direction with MB, VBX, and MB, VBY. Then the collision happens, and the collision happens only in the X direction. There's nothing in the Y direction, because again, the center to center, you connect it together. So that is BF delta T. And as a result of that one, it obtained new velocity. You can say MBV prime BX, MBV prime BY. So now you can see, for this problem, again, you do have a vector in the Y direction. You do not have any vector in the Y direction, because that's X and this is Y. So you do not have any vector in this direction. And so velocity in the Y direction is preserved as long as your collision is a frictionless. Otherwise, if it has a friction, then there is some force in this direction that the ball can basically get off angle, and it goes differently. So you have to be able to find that. So if it's a frictionless, then you can see you have a vector in the X direction, vector in the X direction, vector in the X direction. You have vector in the Y direction, no vector in the Y direction, no vector Y direction. So you can see the velocity in the Y direction is preserved. It's the same velocity that's coming. But in the X direction, you can say MB, VBX. And of course, this one you have to put negative, because if you say X positive, then you put this one negative. But I leave it like that. So you put negative value, negative value. Then you have F delta T in this direction. So this F delta T is in this, and this F delta T is in this direction. So it's the same F delta T, and that's going to be MV prime, MBV prime BX. Only in the X direction that you have. So now you can see that these two forces are in the opposite direction. This force and this force are in the opposite direction to the system. One was a positive X direction, one was a negative X direction. So these two forces are opposite direction. One of the forces here, and the other force is here. So if you add this picture together, it cancels. It cancels. So you can see that this becomes this vector plus the component of this one in the X direction must be equal to this one and this one. You add them up. That becomes conservation of momentum. So you have a conservation of momentum that means says MA VAX plus MB VBX is equal MA V prime AX MB V prime BX. And I solved the problem last time for you, but this equation gives you one equation and two unknown. You have to have some information that when the collision happens, whether these two stick together or these two elastic impact, and that is you have to bring coefficient of restitution. And that means that how the things are hug each other and how they get separated. And through the mathematics, you can show the coefficient of restitution, which should be given to you, is equal to V prime Bx minus v prime ax, vax minus vbx. And that's another thing that you have to have. And if they stick together, that means that after the collision, E is equal to 0. If it is completely elastic, E is equal to 1. In between, some plastic deformations happen and so forth, then E would be different. E is varied between 0 and 1. So last time we made a picture for you that this is obtained some intermediate velocity. So as a result of impact, it obtains some intermediate velocity. So what you have here, when you do have two objects, they hit each other, you do have some intermediate velocity that they are together. At some point, they are together. So that means that they have some intermediate velocity. So you make a picture, you can say is MA, VA. Then you do have some impulse, P delta T. And then you do have some intermediate velocity, not final velocity, MA, V prime A, intermediate velocity. Then rejection happens. Then you start from this picture. Then you do have intermediate velocity, intermediate. Then you do have some rejection, then you obtain MA V prime A. You can do the same thing for particle B, and realizing the P is the same, delta T is the same, R is the same, and so forth, you obtain the second equation. Eliminate intermediate velocity when they are together, and you come with this equation. I did that one last time for you, and look at the notes. Then I start to solve some problem for you, another problem, which we didn't completely finish. So we said that you do have a, let's say, a seesaw, and we assume that this one, let's say this is A, and this distance is a B, and there is a mass here, is sitting here, mass MB. And there is something is coming here with a velocity of VA, and this whole bar, next time I solve for the case that the bar also has a mass. The bar also has a mass. So, and this has no mass, no mass. And this bar comes here, and as a result, this goes fly out. We would like to know what is the velocity of B, particle B, and this has mass of MA. And velocity of the B, we would like to know when it flies out, what is that velocity? So you can say, no problem. You have to consider the entire system. You cannot just concentrate on particle. You have to consider the entire system. So you can say that like this, and that may be a little bit simpler. You can say that this ball is coming with the MA, VA. And we said last time that is, suppose this one come and stick to that bar, a stick. It could rebound. It could be rebound. Then you have to have coefficient of restitution as well and see what's a rebound. But right now, in this case, it's a stick, and that makes life a little bit easier because E is equal to 0, and therefore no problem. So this comes here, and as a result of the impulse, F delta T, it obtains new velocity, and let's say that velocity is in this direction, and is also is equal to MA V prime A. So as a result of if you hit something like this, that is even a zig, that this point may go somewhere. So therefore it has some velocity V prime A, and let's give some number, numerical number. So you can say this is a 2 kilogram, and let's say this one is equal to, I know some of you like the number, you play with the number. Me, I like parametrically, but some of you like the number. So let's say that this is 10 meters per second. So we have all of the number. So MAVA plus F delta T is equal to the bar itself. Now you make a bar. To the bar itself, you can say that there is an impulse. There is no momentum. There is no momentum, and this particle does not have any momentum. Nothing here, and this is your point A that you are holding the structure like here. So now you do have this F delta T comes here. Then you do have some reaction to this one, AX delta T, AY delta T. Before that, you didn't have any momentum, nothing. Everything was zero. And that's your impulse. Now, as a result of that one, this obtained new momentum. And the new momentum that this particle starts to go this way, and that we can call it MB. VB final, and this particle maybe goes, I said, in the X direction, so we put MAV prime A. So this mass stick to here, and it has MAV prime A type situation. So that is your momentum. So, or you can say to the bar itself, forget about this one because I already have considered that one as a separate one. So I don't have to include it again because this is already included. Here is included. And this is my bar, which I just put impulse here. And there is no mass here at this point anymore because it's already I put here. So now if you look at this one, if you add them up to the bar itself, the whole thing, you can see in this side F delta T and F delta T goes away, and to the bar you do have at that location what is left over to the bar. You have the bar, and you look at this end of the bar, what is happening to this end of the bar, what is happening if you add them together. This F delta T and this F delta T goes away. The only vector on this side of the bar that you could have is MAVA. MAVA. That is coming to the bar. And if you add these things together to this side of the bar, to this side of the equation, you do have AX delta T and AY delta T. This is all before the impact. The other mass has no momentum, so no vector here. Nothing. Zero. So this is all before the impact. You put them picture together, and when you put them together, right impact, it has, you have this. You have momentum that's coming to the one. F delta T and F delta T cancel each other. So on this side, you only get all of this thing add them up. So this will be add them up to this location. All of this thing will add up to this location. All of this thing will add to this location. So the next picture is entire system again. Now you do have MA V prime A and only momentum. Only momentum. That's your A. And on this one, your ball is flying. MB BB. So whatever you do to this picture, you do to this picture. Obviously, we are not interested to find AX, AY. You can write it down. Summation forces, summation of vector in the X direction for this picture is equal to summation of vector in the X direction. Summation of vector in the Y direction for this picture is equal to summation. You are not interested to find AX, AY. you can definitely do that. But you can see that for this problem, the best thing is that to take the moment of all of this vector respect to point A must be equal to, these are called equivalent system, moment of all vector respect to point A for this picture. So if you do that, then you will see that becomes MA VA time distance, we call it A, must be equal to, now for this picture, MA V prime A time distance A plus MB VB distance B. Or you can say V prime B, because VB at the beginning that didn't have. You can say V prime B. V prime B. You can, if you would like to say V prime B. So as you see, this is conservation of angular momentum. It's not conservation of linear momentum, because this is R times V, R times mv. And we discuss R times mv is, we call it H angular momentum. So it's not anymore conservation of linear momentum. So now from here, you can say I'm interested V prime B, but unfortunately I have two unknown. I have two unknown, and the question is that I need one more equation. So I need one more equation, and I know the ball is going to stick to that. The ball is going to stick to the right hand side. It's like you have a Play-Doh, stick it there. And now you have one equation, two unknown. So you need one more equation. You need one more equation, and can you tell me what's that equation? Huh? What's that? I heard some noise. So basically, what you have to say, when the bars hit each other and stick here, is a massless, and all of those things that we have. So I stick here, I stick to this location, and this is coming with the V prime A, and this is going with the V prime B, and this is basically R theta dot. So you can say this is R theta dot, and so as this one is R theta dot. So you can say V prime A is equal to A theta dot, and V prime B is equal to B theta dot. So you can say V prime B is going to be equal to B. You eliminate the theta dot between these two equations, and you can say, if you find the theta dot here and you put it here, that would be A or AB. So you can say V prime A over V prime B is equal A to B, or V prime B is equal B over A V prime A, or vice versa. You can find V prime A in terms of the V prime B, or you can say V prime A is equal to A over B V prime B. So that's another relationship that you have. And now you can put it back in this equation. You can put it back in this equation, and you can say MA VA times A is equal MA V prime A, and we assume V prime A is downward positive, and VA is downward positive, V prime A downward positive, V prime B positive upward, and V prime A is equal to A, and that's going to be A over B V prime B, plus MB B V prime B, or you can say V prime B is going to be equal to MA VA divided by MA A squared over B plus mb times b. So if you do have the value of MA and the value of A, you have value of VA, and you have everything here, theoretically you should be able to calculate what is the velocity of the B that is going to take off. And once it takes off, then you can calculate how far it can go up, and you can say the amount that it goes up, h, is equal to square root of, or you can use energy, and you can say 1/2 mb vb square is equal to mgh, mbgh. And you can say that h is equal to s. You can go ahead and solve h. So very quickly, you can go ahead and solve the problem. So the best methodology, even when we go to the rigid body impact, and the best thing is that to see what is going on. And of course, if it has a mass, then we are going to discuss about that one in a few minutes, and when we start rigid body, and we go from that. So you make what is happening before, what is the momentum it has, and of course, if it's a rigid body, it's completely different. We will talk about that one in a few seconds. We'll start right now. And then you do have some impulse, and it obtains new momentum. You do the same thing for everything that you have in your system, and somehow you look at all of this thing, you put the right-hand side together to eliminate some of F, their opposite direction. It's like an equation. You have a certain thing in this side of the equation, you have certain thing in this equation. You add the right-hand picture together, left-hand picture together to eliminate some of the forces that is action and reaction type situation. Then you see what kind of vector left over. And then you can say what I'm going to do with all of this vector that's left over, that I obtain some relationship. And the best thing, what is left over, you can see that is take the moment respect to this point, and by that concept, taking the moment, you eliminate this ax delta t, ay delta t, and that moment is called angular momentum. So in this case, it's not linear momentum that is preserved, it's angular momentum, because you have to say this vector times this distance must be equal to that vector times that distance, and by definition, that's angular momentum. All right, any questions on this problem? All right, so far what we discuss particle, we obtain acceleration, we obtain velocity, we obtain kinetic energy, we obtain impulse and momentum, all of those things that you possibly need for the particle. Now we would like to basically expand this one to the case of the rigid body. So now you do have a rigid body, and this is a capital XYZ, and I want you to pay attention, XYZ, and this is my rigid body, and this is center of the gravity of the rigid body. And this rigid body is moving in space as well as it rotate, So you can say that this rigid body, I can have to put auxiliary coordinate system, a small xyz, to the system. And I like everything in this course respect to to center of gravity. The center of the gravity is the best, okay? Then you don't make a mistake. You can do a respect fixed point, you can do anything you want, but that's the best. And then we show you the methodology again, how to develop the equation motion, and as a matter of fact, we will solve some problem today. All right, so if this is a rigid body that's moving in a space, that means point G is translating. It has some acceleration, and the whole rigid body, it may be rotating with angular velocity omega and omega dot. So maybe the whole rigid body is rotating with angular velocity omega and omega dot. Just think about it like a car. the car has arrived to this distance, so it must have arrived some acceleration, then it's also rotating respect to x, y, z. It has some angular velocity and some angular acceleration. So if we look at any particle, and this rigid body may be subject to some external forces, F1, F2, F3, Fn, whatever. Maybe it's subject to all of these forces, and you are interested, it's like this table. If I push this table, you are interested to see how it is going to translate, how it's going to rotate. That's what you are interested. And predict the motion of the system. Predict the motion. If such a thing happens, where is this object is going to be? So, and that's very important. If you do have a robot, and you are applying some forces to that robot, you would like to make sure what is the motion of this robot, what is the velocity of the robot, what is the distance of the robot, how is it going to rotate, what forces applied to the structure. All of those things you are interested. So you can say, what is this? So we are interested to predict the motion of the system, how the system is moving, and how is the relationship between these forces and angular velocity and acceleration of the center of gravity and all of those kind of things that may be interested. So you can say, okay, no problem. The rigid body is summation of a lot of particles. So you can say this is a particle dm or particle mi. And this particle dm is subjected to a lot of internal forces. So that is subjected to maybe some internal forces. It interact with another particle j. This is a particle I, and this particle I, it has some internal forces, action and reaction. We call it Fij. And it may be some external forces that we call it Fi. So to the particle I, with a mass dmi or dm, we don't have to say I. To this particle I, there are some external forces, which is Fi, or you can say summation of all of the forces, Fi, whatever Fi here is. And there are some internal forces, and that internal forces is in the form of Fij. Internal forces. And as a result of all of these forces, my particle is accelerating. But the acceleration can be defined in terms of rigid body, and acceleration of this point, if it is at the distance rho I, you can say acceleration of particle I is equal to r double dot O plus AXYZ plus 2 omega times Vxyz plus omega dot times rho xyz plus omega times rho xyz. Obviously, rigid body that you have, this point in this coordinate system does not move. So you do not have AXYZ, you do not have Vxyz. The only term that you have is this 3 term that you have. So the acceleration of point is acceleration of center of gravity in this case, center of gravity, because I put my coordinate system right at the center of gravity. So respect to this coordinate rigid body, this point never moves. The whole car is moving, is twisting and moving, but the chair in the car, respect to the car, doesn't move. The chair or the steering wheel, respect to the car, never changes position. All right? So it never had acceleration. Respect to the ground it has, but respect to the car doesn't have. So therefore, I do not have AX, Y, Z. So the acceleration of that point is, you can say, is equal to, this picture is equal to mass times acceleration, and acceleration becomes equal r double dot g plus omega dot time rho plus omega times omega time rho xyz. So this picture is equal to this picture. Or what you can write in terms of vector, you can say Fi plus Fij is equal to dm times r double dot g, these are all vector, omega dot times rho xyz plus omega times omega time rho xyz. So if I write this kind of equation for every particle, for another particle, f star j plus fji is equal dm of this particle I, this particle j, for example, and r double dot j plus omega dot time rho xyz of particle j, this is for j, and plus omega times omega time rho xyz again, and all of those things for another particle. Rho is keep on changing, mass is changing, r double g, and I can write this kind of equation for all of the particle. And if I add all of this thing together, then what happens? If I add all of this thing together, what is this one? Fi, Fj, and I, all of those. What is that? Summation of what? What is that?
External.
Huh?
External.
Summation of all external forces. Summation of all external forces. Summation of all external forces. This side get eliminated. This side get eliminated, and therefore no problem. No problem. It get eliminated. Because I have action and reaction, Fij is equal Fji, it get eliminated. So for any action there is reaction, no problem. Is equal. Now you tell me what is this side is going to be. dmi times r double j, dmj times r double j, and you add them up. What happens? What is that summation? What is that summation? What's that? I didn't hear. I heard somebody say 0. Who says that 0? 0. 0. R double dot j, R double dot j, R double dot j is, you factor it out, you have to add this mass plus this mass, and all of them become mass, right? So it becomes total mass of the rigid body times R double dot g. That shows how is the translation of rigid bodies happen. So that is the total mass of the rigid body, times acceleration of center of the gravity. What happens to this term? Omega dot time rho xyz, omega dot time rho xyz, this mass is here. If I add all of this thing together, what is that? What is that? What is that? Omega is a constant. Omega dot is constant. So basically you have omega dot constant times, you can say integration. Integration of rho xyz, dm. That omega dot is constant. Dm is a scalar, you can put it there. And what is left over is this one, omega dot time rho xyz. That's all you will get. And that becomes integration. What is this integral? What is this integral? Huh? What is this integral? What is this integral? Integration of all of this row times mass. All of this row times mass. All of this row times mass. What is that integral? Huh? Volume? Volume, first of all, the unit is not volume. The unit is not volume. So you cannot say this volume. So what is this integral? What is this integral? Huh? Think about it a little bit more. What is this integral? Huh? Angular momentum. Maybe I should teach another course, therefore, in this class. So you guys are a little bit rusty. And when you are rusty, then that causes a problem. I'm trying to teach you a little bit higher level, and now it seems that you are giving me lower. Give me some energy feedback, and so that's not fair. All right, let's go back to your undergraduate, freshman. Freshman. Sorry to say that. If I give you this particle mass number 1, it is located at x1, y1, and I give you this mass number 2, x2, y2, and I give you mass number 3, x3, y3, and I said, what is the summation of xi mi divided by summation of mi? What does it give you, that one? Huh? Center of the gravity. That tells you where the center of gravity is located. That's a way to find center of it. X rho times dm, you can say x dm, y dm. So for this problem, then it tells you where the center of gravity is located. Summation of xi ai, or summation of xi mi, is divided by summation of mi. It tells you where the center of gravity is located. So with this understanding, can you tell me what the rho x y dm is? What is the value? It should tell you where the center of gravity is located, and it's what? Because it is, I have put the coordinate system right at this location, so this summation must be equal to 0. Should no x, no y. That is basically that from your physics course, how to locate center of gravity and object, xi mi divided by mi. But if your x is equal to 0, the final xg is equal to 0, xg, because respect to this coordinate system, xg has 0 coordinate. That means summation of xi mi, yi mi must be equal to 0. So this number is equal to 0. So if you add all of this thing, the answer is 0. Now if you go to this one, what do we have? Again, you have to see what is constant, what is variable. Your variable is dm as well as rho. So your omega times omega is a constant, so you can say this is equal omega times integration of rho dm again. And again, this one is equal to 0. So that is produce 0. So what you understand, that if you are just interested in the translation of rigid body, where is this car is going without the rotation, where is the center of the gravity is like a point. Where is the center of the gravity of that object is, as a result of translation, if I'm applying some force to this member, and this force, and that's my center of gravity, and I said, where is the center of gravity as my force is applied? You simply write F is equal ma, and that is a differential equation which is second derivative of x respect to this, second derivative of y respect to this, second derivative of z respect to t, or in other coordinate system. And you should be able to say what x and y and z at any time here is based on forces. So it tells you what is that. So that is basically F is equal ma. So for rigid body, we find it out that as a result of forces, summation of forces is equal mass times acceleration of center of gravity, and that gives you the differential equation that you need, that how it is translating. So how is this object is translating in a space, and where is this point at any time? Summation of forces is equal to mass times acceleration of center of gravity. And you better find acceleration of center of gravity of the object, and then you write, and this mass is a mass of the total system. This equation does not tell you how the object is rotating. This equation doesn't. This equation tells you simply center of the gravity from this location, it has gone to this location. It doesn't tell you whether the object is like this, is rotating like this, is rotating like this. It doesn't tell you any of those things. So you need some information that how is the rotation is happening. You just found it out as a result of these external forces, how the system is moving. So here I am, as a result of my muscle forces, I move. But it doesn't tell you whether I have rotated or I have not rotated, whether I have bent here or I have not bent here. So in order to find that one, you have to use concept of angular momentum, maybe, that it relates to the rotation. It relates to the rotation. So now you can say, okay, no problem. No problem. So what we have for every particle that I have, again, I do everything with respect to center of gravity. You can do also respect to a fixed point. Not a problem. But I like center of gravity. And that makes their life much easier. All right? So now again, I go ahead and say for each point, what is going on. So I have Fi. I have Fij, and as a result of that forces that I have, then object obtains some acceleration, which we said Fi plus Fij is equal to dm, mass of this dm, we can call it dmi if you want, and times acceleration, and acceleration becomes r double dot j plus omega dot time rho xyz plus omega times omega time rho xyz. And this omega and omega dot is omega of the rigid body. So now if I'm interested, what's omega? How is the rotation? How is the rotation? So if I multiply both sides this equation by rho xyz, cross product, so I multiply both sides of this equation by rho xyz cross product, and rho xyz cross product. So again, everything comes from Newton's law. I'm not doing anything that you say, oh wow, where it came from. No, we are just interested this time. The first one, it simply said how the object is translated. It doesn't tell anything about rotation. So if I want to have some relationship between those forces and rotation, then I have to do something with to the Newton's law. and see whether I can get some extra, because rotation comes as a result of moment that system is subjected to. Those moments cause the rotation. So force does the translation, moment does rotation. So you said, okay, no problem. For every particle that I have in the system, the particle, and once I develop the equation, then we go ahead and solve a lot of problems. Then if you pay attention, you learn. If you don't pay attention, you will definitely struggle. So you will definitely struggle. You have to pay attention and do the homework, and do a nice homework, not shabby homework. So if you multiply both sides of the equation by rho xyz, that becomes like a moment that is involved with the rotation. So now you can say, okay, no problem. I can write this set of this kind of equation for every point. So I can write another one, rho xyz times maybe fj, fji is equal to rho xyz again of the particle j, this is for particle I, and times dmj, maybe. You can say this is dmi, if you are interested to j and r. Then you can say r double dot g plus omega dot time rho xyz of the particle j. And this is omega times omega time rho xyz of particle j. And if you write all of this equation, and you add them up, what do you end up? So what is this? Rho xyz of particle I times fi. Rho xyz of particle j times fj. What is that summation? What is that summation? What is that summation? Moment of all external forces respect to center of gravity. Moment of all external forces respect to center of gravity. Not a big deal. Moment of all external forces respect to center of gravity. Okay? Very easy. You don't have to be a rocket scientist to do that. So R times F, R times F, R times F, that's a definition of moment. Moment of all forces, rho I times Fi is a moment of all those external forces. Respect to what? Center of gravity, because that's what you are doing. We do everything respect to center of gravity. Makes the life much, much easier. You can do respect to other points too, but then you have to really be in the top of your game. We can develop the equation, but center of gravity is the best. Best. You don't make a mistake. Everything respect to center of gravity. So what is all of these things? What is all of these things? I cannot hear you.
External force respect to the ground.
Moment of external force with respect to center of gravity. So that's a moment. I don't know. Moment of all external forces respect to center of gravity. Moment of all external forces. Now let's go ahead on this side of the equation. This side of the equation. What is this summation? Rho times dm r double dot g, rho times dm r double dot g is a cross product. It's cross product. All of this is cross product. So that's a vector and this cross product. This multiplication is cross product. So what is all of those things? You add them up. What is all of those things that you add them up? What is fixed and what is variable? What is fixed and what is variable? Huh? What is fixed? R double dot G is fixed. R double dot G is not variable. It's a fixed number. What is variable is dm and rho xyz. So you are really doing summation of, again, dm times rho xyz. Again, that is equal to what? 0. That's equal to 0. Okay? So all of this thing that you are adding is R double dot G is a constant. You can factor it out. And rho dm, and then you have cross product. And that rho dm is 0, like what we said. R double dot G is fixed. Doesn't make any difference. So therefore, this summation is equal to 0. Plus. Now this summation, now you do have rho xyz dm. You do have another rho xyz. No, this time rho xyz is appearing 2 times. No, this time rho xyz is appearing 2 times. So you have integration of rho xyz times omega dot rho xyz dm. This one is appearing 2 times. So you do have rho xyz, dm is a scalar. You don't have to put as a part of that. And that would be rho xyz omega dot times rho xyz dm. Now, this is not going to be 0. This is not going to be 0. That has some value. Okay? And in order to evaluate this one, you can say rho xyz is xi plus yj plus zk, and your omega dot is omega dot xi, omega dot yj, omega dot zk times rho xyz xi plus yj plus zk dm. And if you do the multiplication, you end up with a lot of integral in form of x squared, xy, and xz, and all of those kind of things that you end up. And so you end up with. Similarly to this one, again, you do have rho omega times rho xyz. You end up with a lot of integral, and so that it has x squared. It's no longer 0. So I write one of those things, and of course you end up with a lot of integral. Integration of, for example, x squared dm. Omega dot is constant, x squared dm. You get integration of xy dm. You end z squared. You end up with the yx again. You end up with a lot of integral that you have, and those is in this form. Maybe integration of x squared plus y squared dm. You end up with a lot of integral, and those are called mass moment of inertia. Mass moment of inertia that somebody has to tell you for certain geometry. You can find that one. Similarly for this term again would not get eliminated. And if you just do this mathematics, I'm not going to go to the entire mathematics and show you all of the multiplication. Then you end up with the following equation. You end up with the following equation, which is a gigantic equation, and I write one of them only, but I can write for all of the term. And you end up with the component of the moment in the x direction is omega dot x ixx plus omega y omega z izz minus iyy plus ixy omega z omega x minus omega dot y. Then you end up minus ixz omega dot z plus omega y omega x minus I by z omega y squared plus minus omega z squared. And of course Ixx is integration of y squared plus z squared dm. Ixy is integration of xy dm. You have to integrate all of these things and see what is this number. And I can also write for my and mz, but I'm not going to write it because that's a gigantic equation. I can write it down for you, and if you want, I can write it was my, mz. But it's a gigantic equation that relates the moment to the rotation. Now, if you have put your coordinate system, on a symmetric plane, or the structure has some symmetricity, then you can show, if the structure has some symmetricity, then you can show that Ixy is equal Ixz is equal Iyz is equal to 0. So the life becomes much simpler, and your equation becomes much simpler to solve, and the equation that you end up, you do not have any of these things. You do not have this, you do not have this, you only end up with this one. So you can, and the equation becomes, but you have to make sure your structure has a symmetricity, and you put the coordinate system on the symmetric axis. For example, if you do have a bar, you put your x in this direction, you put your y in this direction, you put z in this direction, that's a symmetricity. So in the x and y direction is a symmetricity right at the center. Or if you have a circle, you have to put your coordinate system at this one, it has some symmetricity. So if your rigid body has some symmetricity, then some of this term get eliminated. And the equation that you end up is the following. The equation that you end up, mx is equal to omega dot x Ixx plus omega y omega z Izz minus Iyy. And Ixx, as I say, is integration of x squared, integration of y squared plus z squared dm. This one is integration of x squared plus y squared dm. And this one is integration of x squared plus z squared dm. So for every point of the body, you have to say what's x and y. And if you are doing that one, integration of x squared y squared dm. And in your book, for certain geometry, it is tabulated. So you can look at your book, there's a table, and in that table it tells you what's Ixx, Iyy, Izz for symmetric axis, and we will solve some problem. If you would like to have my is going to be is equal to my is equal Iyy omega dot y plus omega z omega x Ixx minus Izz. Mz is equal to Izz omega dot z plus omega x omega y Iyy minus Ixx. And this equation are called the Euler equation. This equation is called Euler equation. Euler equation. So what do you have to do? What do you have to do when you are trying to develop the equation motion? When you are trying to develop the equation motion of rigid body, so these are called Euler equation. So when you are trying to develop the equation motion of rigid body, right hand side picture you identify all external forces, F1, F2, F3, F4, and you also identify center of gravity. Where is the center of gravity? On the right-hand side, you make another picture. You make another picture, and again, you put on the center of gravity, acceleration of center of gravity, AG. You have to obtain that based on your degrees of freedom as you have to put acceleration center. In addition, you have to put your Euler equation. Your Euler equation. You have to evaluate your Euler, and you put it back on that. So you do have some symmetric axis. You identify some symmetricity. If it is symmetricity, if it is not symmetricity, then you have to use gigantic equation. You have to use that gigantic equation, and I have also for my and mz, but I'm not going to do that. But in many textbooks you can go. I do not know whether your textbook has that one, Euler equation. I think he has put Euler equation for the symmetricity. But if you want, I can write also my and mz for you, that if you do not have symmetricity. But if you do have symmetricity in the three plane, then the life becomes much easier, and some of these terms, Ixx, Iyy, Izz, is tabulated in your book. If it is not symmetricity, then you have to write a computer program to calculate what's Ixx, Iyy, and so forth. You add all of those things together, not a problem. You can do that. I mean, if we have a structure that is not symmetric, no problem. You have that gigantic equation. The only thing that you have to go ahead and evaluate, you can write a simple MATLAB program and say what's the coordinate of every particle, how much is the mass of every particle, and what's the definition of Izz. And you said Izz is x squared plus y squared dm. You add them up, and you do have Ixx. Not a problem, not a big deal at all. I mean, as a graduate student, you are doing PhD, you shouldn't say, oh, for this structure is not symmetric and I don't have a table. No problem. Go ahead and write a small MATLAB program to see what is all of this mass moment of inertia. This is called mass moment of inertia, and that is basically what you have. But if it is symmetricity, it's tabulated in your book, and you do have it. So you put on that one, and you find some axis, and you add mx, my, mz to the problem, and now whatever you do to this picture, you do to this picture. Whatever you do to this picture, you do to this picture, and then you do have your forces. If you know reaction forces, if you are interested. If you do not know external forces, but you know the rotation, so you have all of those things, and you put it, and you find your information. All right, let's solve one problem, then you will understand what I'm talking about. And let's keep that Euler equation here, and then we solve a lot of problems. At least for the next 2 weeks, we solve a lot of problems, then hopefully you will be master in rigid body. Master. I mean, theoretically you should be master, but hey, we'll see. Okay. Here we are. All right, I keep the Euler here. We start with simple problem, and then we go from simple problem. All right. I want to solve a simple problem that you would. All right. So let's say that you do have a bar here, and this is, let's say, is a massless. We can make it mass. And then in the top of that, we have attached a disk. We have to attach a disk here, like this, a disk. And this is a pin here, and the mass of this disk, let's say, is 5 kilogram. The radius of this disk, let's say, is 1 meter. The length of this one is, let's say, 5 meter. Gravity is acting. Gravity is acting. We would like to tell us, and suppose, and this one is also fixed somehow, so that's everything is. We would like to tell us, for this structure that is rotating around this axis, omega and omega dot is rotating around that axis. We would like to tell us what kind of reaction forces are going to develop on the pin. So I'm rotating this one with angular velocity omega and omega dot. You can think about it that you do have some thrust bearing here. You can think about that you do have some thrust bearing, and this is attached to some thrust bearing somehow, that this is rotating around that thrust bearing. Somehow we rotate it around that thrust bearing. Something is come out, and then we rotate it around that thrust bearing. The question is that the hinge itself is like this. The hinge is like this. That's hinge. So you can think about that the whole system is, it has a hinge like this. So you do have a hinge here, and that's a hinge. You can think about that location as hinge like this. Simple problem, maybe. And it's rotating with omega and omega dot. And let's say that this angle, we keep this angle also constant. Somehow this angle, we keep it constant. But we may ask you, what's this angle? What is the equilibrium of that angle? Well, let's keep that one as also. So we don't keep that. We say, what is this angle theta? So the question is that we are rotating this one with constant omega. Let's say we are rotating at constant omega. Then because we are rotating at constant omega, is like that one that I just showed to you before. And so if you have this mouse, and this is, I'm rotating with the constant omega, then eventually maybe some constant angle is achieved, some constant angle. If I'm accelerating, then of course it's not going to be, because then my omega is going to increase, and that may not be constant, and so it keeps on changing. Well, let's make the life a little bit easier for us, and we said like that. So we are interested, first of all, what is the theta? What theta is achieved? What's a theta? How much theta will be based on this rotation of this disk? Is a rigid bar, and I'm rotating like that mouse that I was just dealing. And so I'm rotating that. And what are my reactions at the support? What kind of reaction forces is going to be involved in that one? And force in the x direction, force in the y direction, force in the z direction, possibly moment, maybe in the x, possible moment in y, possible moment in z axis. So, and that's what we are interested. So it's no problem. The first thing that you have to do, you have to say, what is the acceleration of center of gravity. You have to find what's the acceleration of center of gravity, and what is this? Acceleration. So you said acceleration of center of gravity. I put an auxiliary coordinate system here, x, y, z, and my small x, y, z is rotate with the omega. And then I go ahead. And because I assume is that theta is not going to change, then I assume theta dot is equal to 0. But later I can add theta dot, theta double dot, and then I can go to equilibrium and find what is the equilibrium situation, find those things as well. So we may do that. If you would like to say theta is also changing, then I can say theta dot and theta double dot is also exists, and then I can go at the situation that at what theta those are 0. At this speed, what is happening? So let's keep that one also as a variable. So let's keep that one as a variable. So you can say that I have to find acceleration of center of gravity. Acceleration of center of gravity. And you said no problem. Acceleration of center of gravity is defined as r double dot o plus axyz plus 2 omega vxyz plus omega dot times rho xyz plus omega times omega times rho xyz. So for this problem, r double dot o is equal to 0. Acceleration of center of gravity is equal to 0. Acceleration of the center of gravity with respect to a small xyz, what is that? What's that? You must know that.
0.
Huh?
0.
Well, if theta is fixed, it's 0. But if the theta is a variable, then you have two acceleration. One is r theta double dot in this direction. One is r theta dot square in this direction. And I know I'm going to solve for the case that we do have theta as a variable. Okay? So then you cannot say that, okay, if the theta stays constant, then you do not have theta double dot and they do not have anything else. So that would be 0. So I'm solving for general case. For general case. So you can say acceleration of center of gravity is equal to r theta dot, and r in this case is, let's say, L. Again, I like to solve everything parametrically. And L theta double dot E theta minus L theta dot square ER. So you have two acceleration, this and this. Then you do have 2 omega, that is 2 omega capital K. And let's say this is X, Y, Z, capital X, capital Y, and capital Z is also in this direction. Then it would be 2 omega capital J time Vxyz is L theta dot E theta. L theta dot E theta. Then you do have omega dot. For this one is going with the constant velocity. I don't have that situation, so I don't have 0. And then I have omega j times omega j LER. And ER is here. E theta is here. And of course, ER and E theta is related to a small xyz. Is related to the ijk of a small. So from here, you can go ahead and see what's acceleration. Acceleration becomes equal to center of gravity is L theta double dot ER, E theta, minus L theta dot square ER plus 2 omega L theta dot, and J times E theta, this is j, this is e theta, this is pi over 2 minus theta, and j times e theta is in direction of a small k, negative k, a small k, not capital K, because it is xyz. So that is going to be sine theta, that is cosine theta, and the direction of that one minus a small k. A small k. A small k is always going around. A small k is always going around. Then you do have this term, omega j LER, and that becomes omega square L, j times ER. J times ER is this angle, which is again is this angle is pi minus theta, and that will be sine theta, and the direction of that one is negative k. And then you do have j, capital J times a small k is a small I. So you do have sine theta, and that's a small I. So that's your acceleration, and we are also, what's your omega? Your omega, total of the system, is omega capital J plus theta dot a small k. So your omega total is omega capital J plus theta dot a small k. Now you proceed with the free body diagram. You proceed with the free body diagram. Let me just do this one. So that's my free body diagram. That's my member. That's my member. Yeah. And you do have mg here. You have mg here. You have reaction here, ax, ay, az. Your joint may produce some max here, and it may produce some maz here. In the z direction, it is not. Maybe you are supplying some moment. I don't put anything. Right now, I assume it's 0. But if I end up, then I put some moment around that direction too. But I'm assuming that that does not tolerate. But maybe you are supplying some rotation. It's rotating with constant angular velocity, and maybe I'm supplying some torque to keep this system going. So without the torque, how the system moves. So maybe I have some supply torque. So here I can put some my here, or supply torque. Now this picture is equal to, you make another picture like this, you make another picture like this, and now for this problem you put a symmetric axis. You identify symmetric axis, because when you want to put your Euler equation, you put on the symmetric axis. So your symmetric axis here, we can call it x star, y star, it's coming out of the page, z star. Z star. So you have to, I didn't mean to solve this. It turns out to be a little more difficult problem. We solved a much easier problem than this. So very straightforward. You don't have to really worry too much. If you know how to find acceleration and you know how to make a free body diagram, there is no excuse really not to be able. So, and you have to say what's acceleration. Well, it happens that you have acceleration of center of gravity, and you do have lots of term. You have L theta double dot E theta, you have L theta dot square ER. So you multiply all of those things by mass, and you put it as a vector in the situation. So you do have one vector in this direction, mass times L theta double dot. You put one vector in this direction, mass times L theta dot square. You have one is coming out of the page, which is in the direction of K or Z star, and it's coming out of the page, it's coming towards you, and you do have one here, mass times 2 omega minus 2 omega L theta dot cosine theta. And finally, you do have one in this direction, omega square L sine theta in the direction of I. So you can say this is in this direction of a small I. Of course, all the time it's going around, but at this instance, a small I is in the direction of capital I. So you can say you do have one in this direction, mass times L omega square sine theta, which is like a normal acceleration that you have. That point goes around the circle, and L sine theta, and that's basically you have R omega square type situation. But R is L sine theta. So that is all of your inertia term. You have to put in the picture. You have to put in the picture all of your inertia term. So we have a bar like a mouse that I was rotating, and mouse has maybe modeled like a small disc attached to my arm, and I'm rotating here, and I would like to know what kind of force is happening to my hand. And you say, no problem. The forces that's happening to your hand maybe is AX, AY, AZ, maybe MX, MY, MZ. No problem. We have all of those things. And in order to find those things, you have to say, what's the acceleration of center of gravity? You find acceleration of center of gravity. In addition, you identify symmetric axis on that one, and you have to put MX, MY, MZ. But on this axis, on the symmetric axis, because we said respect to the symmetric axis is Euler equation. So you have to say MX, MY, and MZ. You add this one to this picture on this side of the equation. So according to your Euler equation, your MX, according to your Euler equation, your MX is omega dot x. Let me write it down. According to your Euler equation, and when we say x is symmetric, it has nothing to do with the auxiliary anymore. It has nothing to do with the auxiliary. You have to say respect to the symmetric axis that you put on the disk, not auxiliary anymore. So make sure about that, you understand that. So this is respect to this axis that you put on symmetric axis. So mx according to the Euler is equal to, if you would like, I can say a star is omega dot x ixx plus omega by omega z izz minus iyy. Let me erase this one. Now if you go to the table, if you look at the table on your book, if you do have a small disk and this is your x-axis, your ixx is equal mr squared over 2. Respect to this axis, is mr squared over 2. So Ixx, if you look at the table, is mr squared over 2. Iyy, if you look at this one, Iyy is half of it. Iyy is 1/4 mr squared. There is a table in your book, and Izz is equal to 1/4 of mr squared. 1/4 mr squared. So that's not a problem. You can say what is Ixx, Iyy, Izz for your disk. For your disk, that's not a problem. The only problem is that you have, in order to evaluate this mx, you have to say what's omega dot x. What's omega dot x? What is omega y? What is omega z? And then you put it back in this equation. Not a problem. So what is omega x? And then omega x again is respect to your symmetric axis, not respect to the what you had before. This is your omega total. This is your omega total. So what's omega x? What's omega x, omega y, omega z? Well, you have one rotation here, that's capital omega. You have one rotation here in this direction, which is omega theta dot. Theta dot. You have to go ahead and say, in this direction, what is my omega x? You decompose it. You decompose it. So you can say my omega x is really, this does not have any component because it's normal to the page. This has component in that direction. You have to say my omega x, and this angle is a theta, and so as this angle is a theta, so my omega x is minus omega cosine theta. That's my omega x. Because if you are trying to evaluate Euler equation, you have to say omega x, what's omega x? You have to say what's my omega y? Omega y is in this direction. Omega y is in this direction. Omega y, again, this does not have any component in this direction. The only one that has a component in that direction is this omega, which is multiplied by this angle, which becomes the cosine, becomes sine. So that omega y is equal to omega sine theta. And your omega z in this situation is simply theta dot. Omega z is equal theta dot. You have to evaluate all of this thing. You also have to know for the Euler, to evaluate Euler, you have to know what's omega dot x. And if you do have omega dot y and omega dot z, you have to have that one as well. So now you have your omega. What's omega dot? You have your omega. What's omega dot? What's omega dot? No problem. Go ahead and make a derivative of this expression. Go ahead and make a derivative of this expression. You do have omega respect to the ground, and then you can decompose it on symmetric axis. Decompose it on symmetric. So your omega dot is equal to, this is 0, this is constant, never change. This becomes theta double dot. Theta double dot small k plus theta dot, and now you say k dot. K is being twisted by big omega, so omega j times a small k. And j times k is equal to I. J times k is a small I. So that's omega j times k is a small I. So your angular acceleration is theta double dot k plus theta dot omega small I. Again, your small I is in this direction. That's your small I. That's your auxiliary. That's your auxiliary. Has nothing to do with symmetric. So you do have one acceleration in this direction, theta dot omega. You do have one acceleration in this direction, theta double dot. You have to decompose this one in the direction of the symmetric plane. Then you can use Euler equation. So you can say that, again, in the x direction, this is my acceleration, and this is my theta, that's my theta, so that I have. So you can say that, and this angle is theta. So this is pi over 2 minus theta. So my omega dot x, let me erase this one. My omega dot x, is equal theta dot omega. Cosine of this angle becomes sine theta. My omega dot y is equal to theta dot omega, and in this direction becomes theta cosine theta. And my omega dot z, it simply is theta double dot. So you have everything. So you can go ahead and say that my mx star here is omega dot x. That is theta dot omega sine theta. Omega y is equal to omega sine theta, and omega z is a theta dot. You can go ahead and evaluate the Euler equation in the y direction. So my, we can say a star again, so you understand that it's in the symmetric. So that is Iyy omega dot y plus omega z omega x Ixx minus Izz. So if you are designing a robot, you have to know all of the forces that's happening to the joint of robot. And mzz is equal Izz omega dot z plus omega x omega y Iyy minus Ixx. You add these things to this picture. So whatever you do to this picture, you can say summation of all of my forces in x direction for this picture must be equal to summation of all of my forces in x direction for this picture. Summation of forces in the y direction for this picture must be equal to summation of forces in the y direction for this picture. Summation of forces in z direction for this picture must be equal to summation of forces. Summation of moment respect to any point. You take the moment respect to any point for this picture must be equal to summation of moment respect this picture. Summation of moment respect to z direction for this picture must be equal to summation of moment, and summation of moment respect to any axis must be. So whatever you do to the picture on the right hand side, you do the picture on the left hand side, and you have all of your reaction forces. You do have all of your reaction forces that you possibly need to do. Why don't we continue a similar problem next time, but make sure you review the material for this lecture. Even if you didn't completely understand, go and watch the tape again. Make sure how we did that, because we are going to solve a lot of problems.